Scientists combine data from hundreds or even thousands of seismic stations scattered across the globe to construct a three-dimensional image of the mantle. These images reveal variations in wave speed, offering a glimpse into the Earth's interior and subtle gradations of hot and cold, much like a thermal imaging scan. The Hawaiian plume, the enigmatic African superplume, and other prominent features have all been revealed through this powerful technique, transforming abstract seismic data into tangible representations of Earth's inner workings. Through these distant vibrations, we begin to visualize what would otherwise remain invisible: narrow rivers of scorching rock ascending through a planet of solid stone. Mantle plumes, therefore, connect the deepest layers of the Earth to its surface, and seismic waves act as the echoes that narrate their remarkable story. The notion that solid rock can flow might initially seem paradoxical. After all, we typically perceive stone as hard, rigid, and unyielding. However, within the mantle, under conditions of immense pressure and searing heat, solid rock behaves in a manner that defies our everyday understanding. It doesn't melt into a liquid state, but it does move, stretching, bending, and deforming with a slow, graceful rhythm that only becomes apparent across vast expanses of time. This phenomenon is known as viscous flow. Viscous flow is movement that occurs not because the material is liquid, but because it is subjected to such intense heat and pressure that it behaves more like a thick, sluggish syrup than a brittle solid. The rock doesn't crack or shatter under stress. Instead, it slowly changes shape as it flows in convection currents deep beneath the surface. Even at temperatures exceeding 2,000 degrees Celsius and pressures that would effortlessly crush steel, the mantle remarkably remains solid, yet it moves persistently and inexorably. This peculiar in-between behavior is a crucial factor in the Earth's long-term evolution, making the mantle a key player in shaping our planet. Its flow, while imperceptible to the naked eye, is undeniably measurable. Over immense timescales, it transports heat from the deep interior toward the crust, while simultaneously carrying cooler material from the surface down toward the core. These slow, circulating currents drive a multitude of geological processes, from the continental drift to the birth of volcanoes. The consequences of this subterranean movement ripple upward, profoundly affecting the crust, the oceans, and even the atmosphere, highlighting the interconnectedness of Earth's systems. The influence of the mantle on surface geology is expansive and profound. Wherever hot mantle material rises, it exerts an upward force on the crust, creating bulges in the surface that can lead to the formation of plateaus, dramatic rift valleys, or extensive volcanic fields. The East African Rift, for example, is a prime example of this process in action. Here, the crust is being stretched and pulled apart by an upwelling of mantle material, resulting in the formation of deep valleys and a scattering of volcanoes across the region. This process, unfolding slowly over millions of years, is literally tearing a continent in two, reshaping the very face of the Earth. Volcanic activity stands as one of the most visually striking and dramatic outcomes of mantle behavior. When hot plumes ascend from deep within, they melt portions of the upper mantle, generating magma, molten rock that is less dense than the surrounding solid material. This buoyant and scorching magma then makes its way through weaknesses in the crust until it violently erupts at the surface, releasing its pent-up energy in spectacular fashion. Over time, repeated eruptions build up volcanoes, towering landforms that can stretch miles into the sky, influencing regional climate, shaping ecosystems, and even impacting the evolution of life itself. Different types of mantle material give rise to distinct styles of volcanism. Hot, low-viscosity magma tends to create broad, gently sloping shield volcanoes, like those that characterize the Hawaiian Islands, their tranquil beauty belying their fiery origins. In contrast, cooler, more silica-rich magma leads to explosive eruptions characterized by ash plumes, pyroclastic flows, and the dramatic reshaping of the surrounding landscape, as seen in the Pacific Northwest or at Mount Vesuvius. These variations in eruption style are not random occurrences. They reflect fundamental differences in mantle chemistry and temperature that have accumulated over vast geological timescales, a testament to the Earth's complex history. The mantle also plays a critical role in the long-term stability of the crust. In regions where the mantle is unusually hot or buoyant, the crust can become thinner and more stretched, resulting in the formation of rift zones and sedimentary basins. Conversely, cooler, denser regions of the mantle can exert a downward pull on the crust, contributing to the sinking of oceanic plates into subduction zones, where one plate slides beneath another in a process that drives plate tectonics. And the continents themselves are not immune to the influence of the mantle's slow rise and fall. As mantle currents shift and rearrange themselves, they can lift entire landmasses or allow them to subside, causing dramatic changes in elevation. This vertical motion, known as dynamic topography, alters sea levels, reshapes drainage patterns, and influences the evolution of coastlines over tens of millions of years. A constant reshaping of the Earth's surface by forces hidden deep within. So while the mantle lies hidden beneath hundreds of miles of solid rock, its pervasive influence is evident everywhere, in the shape of the land, the placement of volcanoes, the patterns of earthquakes, and the slow, inexorable rearrangement of continents across the face of the planet. It is, without a doubt, the deep molten heart of Earth's surface story, a dynamic engine driving geological change on a global scale. As we prepare to leave the mantle behind and descend even deeper into the planet, we enter a realm of staggering extremes, a world of crushing pressure, unimaginable heat, and metals that behave in ways that no surface material ever could. This is Earth's core, the fiery heart of the planet, hidden more than 3,000 miles beneath your feet, a realm of mystery and power. Though no human instrument has ever penetrated this deep, scientists are remarkably confident about what lies below, thanks to the way seismic waves propagate through the planet during earthquakes. These vibrations act as a form of sonar, revealing not only the shape and depth of the core, but also its unique internal structure, a testament to the ingenuity of scientific investigation. And what they reveal is truly extraordinary. The core is composed primarily of iron, with smaller amounts of nickel and traces of lighter elements like sulfur, oxygen, or silicon. These elements are incredibly dense, and under the extreme pressures of the deep Earth, they form the heaviest part of the planet, concentrated at its center. The core accounts for roughly one-third of Earth's total mass, despite occupying only about one-sixth of its total volume, highlighting its immense density and the incredible forces at play within the Earth's interior. When the Earth first formed, it was entirely molten, a seething ball of liquid rock and metal. Over time, heavier materials like iron and nickel sank towards the center under the influence of gravity, while lighter materials floated towards the surface. This process, known as planetary differentiation, created the layered structure we observe today, with the core at the center, enveloped by the mantle, all beneath the relatively thin crust, a cosmic sorting process that shaped our planet. The core has remained ever since, an ancient remnant of Earth's earliest moments, slowly cooling and evolving beneath layers of rock, a geological time capsule holding clues to the planet's formation. But the core itself isn't a single uniform entity. It's composed of two distinct layers, separated not by composition but by their state of matter. The outer core, approximately 400 miles thick, is liquid. It flows like a molten ocean of metal, churning and swirling due to the heat rising from the deeper Earth, a dynamic sea of liquid iron and nickel. Beneath this liquid layer lies the inner core, a solid sphere with a radius of about 760 miles, roughly the size of the Moon. Here the pressure is so intense that iron remains solid despite temperatures that may far exceed 10,000 degrees, a testament to the power of pressure to alter the properties of matter. This contrast, liquid outside, solid inside, is one of the most remarkable and intriguing features of Earth's interior, a geological paradox born from extreme conditions. The outer core, behaving more like a fluid with its currents and eddies, plays a vital role in generating Earth's magnetic field, a protective shield that deflects harmful solar radiation. The inner core, in contrast, is rigid and dense, slowly crystallizing over time as the Earth continues to cool, a testament to the planet's ongoing evolution. The boundary between these two layers is sharply defined. Seismic waves react very differently when they transition from liquid to solid or vice versa. S waves, for instance, are unable to propagate through liquids, so they disappear entirely within the outer core. P waves, on the other hand, continue through, bending and changing speed as they move through materials of varying densities. By meticulously studying these changes in seismic wave behavior, geophysicists have mapped the precise edges of the core and confirmed its dual structure, providing invaluable insights into the Earth's interior. Though sealed away beneath thousands of miles of solid rock, the core is not isolated from the world above. It plays a crucial role in many aspects of Earth's behavior, particularly in protecting life on the surface, a story we'll continue to explore as we delve deeper into the planet's mysteries. The deeper we venture, the more extreme the conditions become. At the very center of the Earth, more than 6,000 kilometers beneath the surface, the environment is unlike anything else on the planet, a realm of unimaginable extremes. Here, the temperature is estimated to reach a scorching 10,000 degrees, hotter than the surface of the sun. Yet the pressure is so immense, over 305 million times greater than atmospheric pressure at sea level, that even metal behaves in unfamiliar ways, defying our everyday expectations. This extraordinary environment, iron crystallizes into a solid form despite the intense heat. At the Earth's center, atoms are packed so tightly together that the structure of the inner core is thought to be mostly solid iron, with small amounts of nickel and possibly other light elements compressed into an incredibly dense state. The pressure, the material, because this is, as it moves, driven by heat and the planet's slow rotation, it sets up circular currents like eddies in a giant metallic sea. These currents in turn generate magnetic fields through these were what make on Mars, but on high energy in a very the magnet without it is the when it without even more thanks to when's these are, and yet for something so essential, the core remains profoundly out of reach. No probe has ever visited it, and no drill has even pierced the outer layers of the mantle, let alone the core, highlighting the immense challenge of directly studying the Earth's interior. So, how do we glean information about what's hidden so far below? The answer lies in a combination of ingenious indirect methods, particularly seismology and geomagnetism, two of the most powerful tools in the Earth science arsenal. Seismology is the study of vibrations within the Earth, especially those generated by earthquakes. When a quake occurs, it sends out waves that travel through the planet's interior, carrying valuable information about the materials they encounter. These waves move at varying speeds depending on the type of material they pass through, and they bend or reflect when they encounter boundaries between different layers, providing a map of the Earth's internal structure. By meticulously studying how seismic waves behave as they traverse the Earth, scientists can reconstruct the internal structure of the planet, including the size, density, and state of the core, unlocking secrets hidden for billions of years. Two primary types of seismic waves are utilized: P waves, which can travel through both solids and liquids, and S waves, which can only propagate through solids. These two types of waves act as complementary probes, revealing different aspects of the Earth's interior. When S waves fail to appear on the far side of the planet after an earthquake, it reveals the presence of a liquid layer, in this case the outer core, demonstrating the power of seismic waves to distinguish between solid and liquid regions. P waves, meanwhile, slow down and bend as they pass through the liquid outer core, then speed up again as they traverse the solid inner core. These changes in speed and direction provide precise measurements of the core's depth, shape, and composition, allowing scientists to create detailed models of the Earth's inner structure. Geomagnetism, the study of Earth's magnetic field, offers another window into the core's behavior. By tracking changes in the field over time, scientists can model the flow of molten metal in the outer core, gaining insights into the geodynamo process. Fluctuations in magnetic strength and direction reveal how the core currents are shifting and how the geodynamo is evolving, providing valuable data on the Earth's internal dynamics. Satellite missions such as the ESA's Swarm constellation continuously monitor the magnetic field, capturing its subtle variations with extraordinary precision, allowing scientists to track the ever-changing magnetic field in real time. These techniques, combined with high-pressure laboratory experiments and sophisticated computer simulations of core behavior, give us a surprisingly detailed understanding of a place we cannot directly access, a world of metal, heat, and motion sealed away at the center of the Earth. Despite all that we've learned about the Earth's core, it remains one of the most enigmatic regions of our planet, a realm we know only through vibrations and magnetic whispers, a place where mystery still reigns. Many of its behaviors are not yet fully understood, and each discovery seems to unveil a new layer of uncertainty, a reminder of the vastness of what remains unknown about our planet. One such puzzle is the rotation of the inner core. Seismic data suggests that the solid inner core may rotate slightly faster or slower than the rest of the planet, a phenomenon known as differential rotation, adding another layer of complexity to the Earth's dynamics. Some studies suggest it speeds up or slows down in cycles that may be linked to changes in Earth's magnetic field, hinting at a connection between the core's rotation and the geodynamo process. However, the exact cause, rate, and effects of this motion remain a subject of ongoing debate and research. Even the age and formation of the inner core is a matter of scientific inquiry. While the Earth itself is over 5 billion years old, the solid inner core may have formed much more recently, perhaps only 5 billion years ago, as the planet slowly cooled enough for iron to crystallize at the center, a relatively recent development in Earth's history. This relatively late formation could explain the strengthening of the magnetic field in Earth's more recent geological past, providing a possible link between the inner core's formation and the evolution of the magnetosphere. Another mystery lies in the asymmetry of the inner core. Seismic waves travel at slightly different speeds depending on the direction they pass through it, indicating that one side of the core may be cooling or growing faster than the other, a structural anomaly that challenges our understanding of the core's dynamics. Some researchers propose that heat may be escaping unevenly or that compositional differences exist between the eastern and western hemispheres of the core, but so far no model fully explains the observed data, highlighting the need for further investigation. There is even compelling evidence that layers exist within the inner core itself, a solid inner core with different crystal orientations or structural properties, adding another layer of complexity to the Earth's deep interior. This would suggest that the deepest part of the Earth has its own unique history and internal complexity, a kind of planet within a planet with dynamics still unfolding, a testament to the Earth's hidden depths. And so, as we prepare to leave the core behind and journey outward once again, we do so with a sense of humility, acknowledging the limits of our current knowledge. For all our advanced tools and sophisticated models, the heart of the Earth remains largely unknown, a realm of fire and metal spinning in silence far beneath our feet. To fully understand the engine that drives Earth's internal processes, the drifting of continents, the rise of volcanoes, and the subtle motion of the crust, we must turn our attention to a single fundamental force: heat. Heat is the driving force behind it all. It keeps the mantle moving, fuels the geodynamo in the core, and powers the ongoing renewal of the planet's surface. But where does this crucial energy come from? There are two primary sources of heat inside the Earth, each playing a vital role in shaping our planet's destiny. The first is primordial heat, energy left over from the violent birth of the planet, a legacy of Earth's tumultuous beginnings. Over 5 billion years ago, the young Earth formed through collisions, mergers, and gravitational compression of smaller bodies in the early solar system, a chaotic process of accretion and growth. These impacts released immense amounts of energy, heating the growing planet until it was completely molten, a fiery crucible forging the Earth in its earliest stages. As the planet cooled and solidified, much of that original heat was retained in the deep interior, trapped within the Earth's core and mantle. This primordial heat has been slowly leaking out ever since, flowing through the mantle and crust and eventually radiating into space, a gradual dissipation of Earth's birth energy. But this primordial heat alone hasn't been sufficient to keep the Earth geologically active for billions of years. The second major source of heat is radioactive decay, a steady long-term energy source that continues to warm the planet from within, providing a constant supply of thermal energy. Certain isotopes are naturally unstable. As they decay into more stable forms, they release energy in the form of heat, like tiny subterranean nuclear reactors powering the Earth's internal processes. These radioactive isotopes are found primarily in the crust and upper mantle, and their decay provides a continuous source of thermal energy. This heat drives mantle convection, supports volcanic activity, and sustains the magnetic field by powering convection in the outer core, a testament to the long-term influence of radioactive decay. Together, these two sources, the fading embers of a violent origin and the steady burn of radioactive elements, keep the Earth alive beneath its rocky surface, ensuring its continued dynamism and activity. Heat is always on the move. In every part of the Earth's interior, from the crust to the core, energy flows from warmer regions to cooler ones, a fundamental principle of thermodynamics at work. And while the sources of heat inside the Earth are important, it's the movement of that heat that truly shapes the planet. driving geological processes and shaping the Earth's surface. Scientists have identified three primary ways that heat is transferred through the Earth's interior: conduction, convection, and radiation, each playing a different role in the Earth's thermal dynamics. Conduction is the transfer of heat through direct contact, a process that occurs when molecules collide and transfer kinetic energy. It's the same process that warms the handle of a metal spoon placed in hot soup. In Earth's interior, conduction allows heat to flow from one layer to the next where the material is solid and relatively stationary. For example, heat conducts slowly from the hot mantle into the cooler base of the crust. Because rocks are not particularly good conductors of heat, this process is slow, but it's steady and allows heat to gradually rise through static layers, playing a crucial role in the Earth's overall thermal balance. Convection, on the other hand, is the transfer of heat through the motion of a fluid, or in Earth's case, solid rock that flows over extremely long periods. As mantle rock is heated from below, it becomes slightly less dense and rises towards the surface. Cooler, denser rock then sinks downward, creating circular currents that carry heat upward and cooler material back down, a process analogous to boiling water in a pot. This is the dominant heat transfer process in the mantle and outer core, driving plate tectonics and sustaining the geodynamo, a testament to the power of convection. Radiation is the transfer of energy through electromagnetic waves, a process that doesn't require a medium to propagate. It's how heat from the sun reaches the Earth, traversing the vacuum of space. Inside the Earth, radiation plays a smaller role in heat transfer compared to conduction and convection. However, it does occur within the core and to a lesser extent at the atomic scale throughout the Earth, contributing to the planet's overall thermal budget. Most of the heat transfer within the Earth, however, occurs through conduction and convection, especially in the deep mantle, where these processes power nearly every aspect of geologic change. Think of the mantle as a colossal engine room, where heat is the fuel and the constant churning is what drives the ever-evolving face of our planet. It is convection, more than any other mechanism, that orchestrates the grand movements of Earth's surface. The heat rising from the deep interior, whether fueled by the slow burn of radioactive decay or the lingering warmth from the planet's primordial origins, causes mantle rock to circulate in enormous looping currents. Imagine vast sluggish rivers of molten rock, flowing imperceptibly slowly but with unimaginable force. These mantle convection cells are indeed slow-moving material at rates of just a few inches per year, but don't let that pace fool you. This slow creep has sculpted continents, raised mountain ranges, and carved out ocean basins over millions of years. And because the tectonic plates float atop the upper mantle, like colossal rafts on a sea of magma, they are inexorably carried along by these same currents. Where mantle material rises, it creates divergent boundaries, regions where tectonic plates are pushed apart. Mid-ocean ridges are a prime example. Long undersea mountain chains where magma from the mantle wells up and forms brand new crust. These ridges, like the Mid-Atlantic Ridge, are essentially underwater volcanoes continuously adding to the ocean floor. As this new crust spreads outward, older crust is pushed away from the ridge, causing the plates to drift slowly in opposite directions. This process, known as seafloor spreading, is the engine that drives continental drift, the slow ballet of continents across the globe. Where mantle material sinks, usually as a result of a descending cooler plate, convergent boundaries form. Here, one plate is forced beneath another and pulled down into the mantle in a process known as subduction. Picture one massive slab of Earth sliding inexorably beneath another like a slow-motion collision of titans. This sinking plate carries with it water, sediments, and crustal material which melt under the intense heat and pressure and fuel volcanic activity above. These subduction zones are the sites of deep ocean trenches, explosive volcanoes, and powerful earthquakes, all driven by the slow churning of the mantle beneath. The Ring of Fire, that notorious zone of seismic and volcanic activity encircling the Pacific Ocean, is a testament to the power of subduction. Even so-called stable continental interiors are not immune to this movement. The rising and sinking of mantle material can cause whole regions to swell or sag over geological time, lifting plateaus, opening rift valleys, or altering drainage patterns. The African Rift Valley, a vast fracture in the Earth's crust stretching thousands of kilometers, is a dramatic example of this phenomenon. The connection is profound. Heat becomes motion, and motion becomes the sculptor of the planet's surface. Every mountain, every basin, every shifting fault line is a response to the silent, steady rise of thermal energy from within. And though we may walk the surface in stillness, the deep earth is always moving, a dynamic, restless realm hidden beneath our feet. Deep within the earth, heat does more than move. It builds pressure, melts rock, and fuels some of the most dramatic processes we see on the surface. One of the most visible expressions of internal heat is volcanic activity, where molten rock formed in the mantle or lower crust makes its way to the surface and erupts as lava, ash, and gas. Volcanoes are, in essence, the Earth's way of venting its internal pressure. Volcanoes exist because Earth's interior is hot enough to partially melt rock. In subduction zones, water and minerals carried downward by a sinking plate lower the melting point of surrounding rock, allowing magma to form. In rift zones, where plates are pulled apart, the pressure drops rapidly, also causing rock to melt. And above mantle plumes, rising columns of hot material create hot spots, fixed points where magma pierces through the crust over and over again. The Hawaiian Islands, a chain of volcanic peaks stretching across the Pacific, are a classic example of a hotspot. When magma rises, it collects in chambers near the surface. Pressure builds as gases within the magma expand until the rock above can no longer contain it. The result can be a slow ooze of lava or a violent explosion depending on the magma's temperature, composition, and gas content. Each volcanic eruption is the final stage of a long journey that began with heat rising in the deep earth. Quieter settings, that same heat powers geothermal activity. In places like Iceland, New Zealand, and Yellowstone National Park, groundwater seeps deep underground, where it is heated by underlying magma or warm rock. This superheated water then rises back to the surface, emerging as geysers, hot springs, steam vents, or boiling mud pools. Yellowstone, with its geysers, fumaroles, and colorful hot springs, is a stunning showcase of geothermal power. Though these features may seem gentle compared to volcanoes, they are fed by the same forces, a continuous low-level release of Earth's inner heat. Geothermal energy is one of the few ways humans have tapped directly into this internal warmth. Some regions, wells are drilled to access hot water or steam, which can be used to heat buildings or generate electricity. This energy is clean, sustainable, and nearly limitless as long as the planet continues to cool from within. But this flow of heat is incredibly gradual, only a few hundredths of a watt per square meter on average, but across the entire surface of the Earth, it adds up to a significant loss. The planet's energy balance is complex. While it still receives energy from radioactive decay and retains some primordial heat, it has been cooling since its formation. 4 billion years ago, the Earth was far more geologically active, with more frequent and massive volcanic eruptions, a thinner crust, and a hotter mantle. Plate tectonics likely operated differently then, and the core's behavior may have been more chaotic. As Earth cools, changes continue. The inner core is slowly growing as more iron crystallizes from the liquid outer core. This process releases additional heat and light elements into the outer core, helping to sustain the geodynamo for now. But over billions of years, as radioactive elements decay and the core loses energy, the planet will become geologically quieter. The magnetic field may weaken. The mantle may slow, the plates may one day grind to a halt. That time is unimaginably far in the future. For now, Earth remains a living planet, its internal heat flowing outward, powering motion, change, and life itself. Though it lies hidden deep within the planet, Earth's internal heat has effects that stretch far beyond the mantle and crust. One of its most far-reaching influences is on the magnetic field, which is not constant or fixed, but dynamic and ever-changing. These magnetic fluctuations, from subtle drifts to full reversals, are ultimately powered by heat flowing through the core. The movement of molten iron in the outer core, driven by convection and influenced by Earth's rotation, is what generates the magnetic field, but this movement is shaped by how heat escapes from the core into the mantle above. When heat flows efficiently out of the core, for example, in areas where the lower mantle is cooler and more stable, convection in the outer core becomes stronger and more organized. This strengthens the magnetic field and increases its stability. But in regions where the mantle is hotter or more sluggish, the flow of heat from the core can slow down. When that happens, convection in the outer core becomes less vigorous, and the magnetic field can weaken or become more chaotic. These regional variations help explain why the